Hello, my name is Zeel and I'm an undergraduate student in second year, and today I'll be explaining you the Floyd Warshall algorithm. So, the introduction. Floyd Warshall algorithm is basically finding the shortest path, like the most optimal path, which would result in the lowest time of travel in the whole algorithm. So, the algorithm is utilized to track down the briefest ways between all set of vertices in a graph, where each edge in the diagram has a weight, which would either be positive or negative. So, and this algorithm is also called WFI algorithm and Roy Warshall algorithm, the people who founded it. So, this algorithm follows the principle of dynamic programming to estimate the shortest paths. So, let's see. The input given is given a weighted graph G with vertex set V and edge C. Now, V here represents set of all vertices and E is a collection of pairs. Ij representing an edge from I to j. And the problem here is that we have to find the weight of shortest path for all possible pair of vertices. So let's assume a graph with vertices v, 1 to n, and sp ijk, which we are taking a function. So which is weight of the shortest path from vertex I to j, which can have vertices from 1 to k as well as intermediate nodes in that shortest path that we are finding. So the final solution of the shortest path from vertex I to j would be the function of ijn, the sp, that is weight of the shortest path from I to j, which can have any vertex as the intermediate node. So now we are finding sp, the function for n vertices. So for example, this we have taken the figure. So this has in this figure, so the function given here is for ij, 1, 3 and 2. So weight of the shortest path from vertex 1 to vertex 3, which would be this, and which can have vertices 1 to as intermediate vertex. So 1 and 2 would be intermediate vertex. So where we are moving from here to here, we are having this distance as 7. You're seeing here 1, 2, 3, and 1 and 2 are intermediate vertexes. So in the same way, 1, 3, 4, 1, 3, 5, we have 4 and 4, and 1, 3, 0 is infinity because no intermediate vertex is allowed, and vertex 1, 3 and 1 and 3 are basically not connected. So similarly 1, 3, 1 is also infinity, and similarly 1, 3, 2 we have obtained 7. This is 1, 3, 2, yes, we have obtained 7. 1, 3, 3 we have also obtained 7. 1, 3, 3. Similarly, moving forward, so let's now analyze this algorithm a little differently, and let's devise the whole method thoroughly. So let's take a graph and try to find the shortest path within all pair of vertices in a bottoms up manner. So that is, initially we have to try to find the shortest path from vertex I to j having only direct edges. Then we will try to find from vertex I to j which have vertex 1 as intermediate vertex. Then we try to find the shortest path from vertex I to j which can have 1 and 2 as intermediate vertices, which we just did before. So like the final answer would be the function of spij, and that is v mod of v, which is number of vertices. So here we have taken another example. So this is a base case. So between any two vertices, there is no intermediate vertex and only direct edges we have seen here. So where spij of 0 for LA will look like this. Okay. So this is the matrix that would be constructed, and we'll analyze this matrix further and how it's constructed. So the matrix spi of j is denoting the shortest path from vertex I to j and no intermediate vertex because it's only direct edges, and blank cells represent infinity here. So analyzing here now, that's the vertex, that's the matrix that is in here. So basically spij1, we're finding that is shortest path within all pair of vertices which can have only vertex 1 as the intermediate node. So here we are using this spij of 0. Now we'll find out accordingly the matrix, each cell will fill with a value accordingly where we are finding this. So applying this basic formula here, we're finding minimum of the vertices and their distances and filling up the cells accordingly. Here see where, for example, here this is given, we are following the same pattern here as well, sp 5 to 1, so minimum of sp 5 and 0, 1 to 0, and which is 5 to 0. We are here calculating the intermediate vertices and the intermediate nodes which are coming in between us. Okay. So this is minimum of 3 plus 2, which is the distance, and we have or This is like infinity because they don't have direct contact, so that would be 5. Similarly, we are finding other things to fill in the cell here and here. Going forward, now we are finding for SPIJ 2. So that is shortest path between which can have vertex 1 and 2 as intermediate node. Similarly, what we did before, we are doing it here as well. So 132 and 142 we are finding, and we are getting 5, 6 here, 5, 6 and 5 we are finding it here, and similarly we are filling the other cells. Okay. Similarly, we would have to find it for SPI 3, SPIJ 3, 4, and then we have to find for SPIJ 4. That is again shortest path between all pair of vertices, which would have 1, 2, 3 and 4 as intermediate nodes. Applying the same formula we applied before, the intermediate nodes, putting them, assigning them values, the distance, and then distance, which is, and this is the number of vertices, and basically getting the value. So here there are no outgoing edges from vertex 4, so there is no update in the shortest path matrix, which is quite obvious. So, and then we are constructing for SPIJ 5, that is shortest path, which would have all of them as intermediate nodes. Similarly, putting the same formula, having the intermediate nodes, and constructing the following matrix. So yeah, that would be it for that explanation. Now coming to the basic part and some information regarding this algorithm. So when we are putting up this algorithm, which we have just seen that we are using this formula before as well for calculating each cell and putting up distances and finding the minimum distance, which would give us the shortest path. So this loop we are applying in a code. So this is, so basically the complexity where we have seen there are 3 loops used, everyone with a constant complexity. So that would result in O of n cube, the time complexity, and the space complexity for this would be n square.